Okay, hello everyone. I'm going to go through the practice SAC that I gave you in class the other day. My cat Jane has decided to make an appearance, so I'm just going to have to deal with that. She'll probably pop in and out of the video as we go, but yeah. So let's work through this and see how we go. This is the 2020 SAC. We're doing it as a practice SAC. All right. So we'll start off with the multiple choice section. Let me get my CAS up. Hopefully this can be seen okay. I'm trying to put it about there. Okay, so we start with our multiple choice section, and we're looking at a scatter plot, and it shows what type of correlation. Now, yes, hello. It's obviously a negative because we can see that there's a sort of an ongoing decline in the general trend there, and I would argue that it's pretty strong, purely because they're quite clumped together. So I would be choosing a strong negative correlation for that question. Okay. I just want to make sure that I've got this in shot okay. Yeah, I do. Cool. Alright, let's put that back. Okay, a rubber ball is dropped from varying heights, and the height to which it bounces is recorded. The explanatory variable will be. Now, remember, explanatory explains the effect of the response or the change in the response. So in this case, you got to think, does changing the height that you drop the ball change the height that it bounces, or does the height that it bounces changes the height that you drop the ball? Right, and one of those makes more sense than the other one. Right, the height that the ball is dropped from explains the response in how high it bounces up. Okay, so the height the ball is dropped from is the explanatory variable, and the bounce back is the response, or the height of the bounce is the response. Okay, this one it says the weights and lengths of 12 fish are recorded and plotted in a scatter plot below. The least squares regression line that enables the weight of these fish to be predicted and their length has also been plotted. Okay, least squares regression line predicts that weight in grams of a fish that weighs 30 centimeters would be, with a length of 30 centimeters. So if this is length, we're looking at about there, which sort of matches up with, I'd say that, probably that little titch there, which is what, 260-ish. Looking at those, 262 is definitely the closest, so that's what I would be going for. Okay, the lengths and diameters of sample jellyfish. A sample of jellyfish are collected from a location and recorded in the scatter plot. These are the least squares regression line. And we actually get the regression line this time. The correlation coefficient is R equals 0.9034. Written as a percentage, the coefficient of determination is closest to, right? Now, the correlation coefficient is R. The coefficient of determination is R squared, meaning that we just need to do 0.9034 to the power of 2, and that should give us our coefficient of determination. Written as a percentage means we have to multiply by 100 to take it from decimal to percentage, meaning 81.6% is what we're looking for, which is C. From the least squares regression line, it can be concluded that for jellyfish on average, all right, so this is talking about interpreting the what would you call it? I guess the coefficient that goes alongside the variable there. So it's talking about interpreting this value here, right? There is a possibility that it's interpreting that one, but I think it's going to be interpreting this. So there is a 3.5 millimeter increase in diameter for each one. And that's not what we're looking for, because what's happening is it's starting at 3.5, and then for each increase in one diameter, we actually go up by 0.87. There is a 3.5 millimeter increase in length for each 1 increase in diameter. That's not true either. So I suspect that it'd be one of these two, just because they both mention the actual gradient there. There is a 0.87 millimeter increase in diameter for each millimeter increase in length. Okay. Or there is a 0.87 millimeter increase in length for each 1 millimeter increase in diameter. I think that that's the correct one here, because essentially if we go up by 1, right, and we increase this by 1, so the diameter is going up 1 millimeter, this will increase by 0.87. So for example, right now it's 0.87. If I increase that by 1 to 2, this then becomes the 1.74, which is a 0.87 increase, obviously with that included. But yeah, so that would be D. Cool. All right, the length and wingspan of 8 commercial airplanes are displayed in the table below, correct to 4 decimal places. Pearson's correlation coefficient for this data is. So for that, I need to go into list and spreadsheets. If it'll load, good. And I need to type in our data. Okay, so I've entered in all that data there, and now I've got to enter in the wingspans. Okay, so hopefully I've entered in all that data correctly. Now to find the correlation coefficient, we go Menu, Statistics, Stat Calculations. We want to find our linear regression. I didn't give these any names. Whoops. This is length, let's call it L, and wingspan W. Let's try that again. New stats. Stat calculations, linear regression. So our X, remember, explains the change in Y. So I would suggest that the length explains the wingspan and not so much the other way around. I'm sure they designed the hull of the plane first. So there are our values there. We have an R squared, which is our determination, and our R, which is 0.9681, which is this one here. Right, and it's 81 because you'll see the next number here is 5, which means we're actually rounding up from 0 to 1. All right, extended response. I've got another one of these. Let's close this one if I can. Is it going to let me? So I'm having some. Okay, I'll just have to make a new one, I think. Alright, new spreadsheet. This one's going to be arm span and height. And we have our arm spans that we type in. Oops, I made a mistake there. 152, 143. Okay. Now we do their heights. Oh, I stuffed up big time there. Must have got confused. I did here. What was that up to? 157, 163. This was 165. Okay. There should be equal amounts of data. So that was easy to pick up that I stuffed up. Okay, so I'm going to need that eventually, I assume. State the explanatory variable. Well, you would assume that height explains arm span and not necessarily the other way around. So the explanatory variable in this case is height. Assuming there's a linear association, determine the equation for the least squares regression line. Yeah, cool. So that's what I was already doing. Oops. So I'm going to do the same thing as before. Stats. Stat calculus. Oh, if I stuff something up here. Oh, it's probably because I'm still in that box. Let's try that again. Stats, stat calculations, linear regression. We have our explanatory is height. Our response is arm length. So this gives us this equation here. So what I'm going to do is I'm going to write this out, but rather than using m and b and y, m and b, I'm going to use, or x as well, I'm going to use the proper variables here. So if y is arm span, we're going to say arm span is equal to, now the m is 1 point, what am I rounding to here? 2 decimal places. 1.09 times height, and then our b is minus 15.6, and I'm rounding down, so 6.3. So that's it there. Using the equation in part B, determine the slope of the least squares regression line. In using, so I got to explain what it is. Yeah, sure. So I can do that. So the height's in centimeters. So what the slope would mean was for each 1 centimeter increase in height, arm span increases by 1.09. Cool. So that's there. I just want to make sure that's all in shot. Yeah, cool. So that's that will get you those marks. Let's move on. In the mountainous region, a drainage system consists of a number of basins flowing through them. The basins formed by the flow of the river, a random sample of 6 basins. The area of each basin and the total length of the rivers flowing to each basin are as follows. What is the response variable? Well, this is a good question. So, the basins are formed by the flow of the river, meaning the area is the response and the river must be the explanatory. I assume so. Yeah, I'm assuming that the river length has the effect on the area of the basin. So the area is the response in this case. That's a tough one though. Okay, construct a scatter plot of the data. So we have area and river length, and let's do our scatter plot. So area is 7, river length is 10. We have 8 and 8. We have 14 and 9. We have 20 and 16. 11 and 12. And 15 and 13. Wonderful. Larger areas associated with longer river lengths. Explain your answer in mathematical terms. Okay. So it's not necessarily specific as to which one you have to use. I would say that the correlation coefficient is the best one to explain just just how related they are. Please don't type anything. So what we might do, we're going to have to make another one of these. I'm not sure if I can like close these. I wonder if the variables save or not. She just found my pen. I was playing with my pen. Okay, so let's try that. Let's try area, and you're coming up. Okay, and river length, which can't have any spaces in it, mind you. So area, we've got 7, 8, 9, 16, 12, 13. And for river length, we have 10, 8, 14, 20, 11, and 15. All right, let's do our correlation coefficient. Just by looking for a linear regression, we said that our area, oh no, it's the other way around, sorry. Our river length decides the area. So we have that. Wonderful. Which gives us our R value here. So if I were to answer this question, I would say yes, there is a strong positive linear relationship based off the correlation coefficient of 0.84. So I think that it's only worth 2 marks. So I'm assuming it's 1 for saying yes and 1 for the correlation coefficient, but it could be 1 for the strong positive linear. So I'll just include it anyway. It's not like you're going to lose marks. All right, and we have another question which will require me to do my list and spreadsheet, I believe. Oh. Thank you, Jane. You're making this very easy. Okay, so we have the months and the age in months and the results. Teacher constructed this scatter plot. Write down 2 reasons why it is appropriate to fit a least squares regression line to this data. I would say both both variables are numerical. Numerical, and there are no clear outliers. Right. So it's based off the assumptions that you make when you do this sort of analysis, which is essentially saying that you assume that the relationship is linear, and the other part is that there are no outliers and both variables have to be numerical. So I think any two of those three would have been acceptable. I'm losing my place already. Far out. 142. One of the things I dislike about this topic is that if you put in just one piece of data wrong, you can really stuff yourself up. So just got to be careful. Okay, so that's it there. We do our least squares regression again. Now we're going to say that I'm assuming that, I didn't name them again, far out. That's age and mark. So we'd be saying that age is the explanatory and may have some effect on their mark. And that gives us this equation here, which is result equals, our gradient m is 1.57, that's one decimal place, so it's 1.6 times age, and our y-intercept is minus 191.3. Okay, that's that done. Hopefully I didn't stuff any of that up. Find the coefficient of determination for this data. Coefficient of determination is this r squared value. Correct to 4 decimal places. That's 7829, and the next one's 8, so 7830. 7830 is the correlation coefficient. The coefficient of determination. Interpret it in terms of the variables age and result. We can say that 78.3% of variation in marks can be explained by variation in age. Alright, and that's all that coefficient of determination tells us. Alright, next one. We have another thing to do it, put in my CAS. It's getting a bit tedious, that's all right. What do we have this time? We have height and weight. Where did I get that from? 165, 168. Oh my goodness, what am I doing? 193. There's only 7 people. Yeah, right. Seems like an odd number to do a study on. That's okay. 55, 61 and 102. All right. So looking to see if you can predict weight based off height. It makes sense that weight is the explanatory because it's more likely that height would affect your weight than vice versa. Correlation coefficient. We're getting pretty good at this now, I think. SAC calculations, the regression. We're saying that height explains weight. Okay. Which gives us a correlation coefficient of 2 decimal places of 0.99. Yep. Interpret the meaning of correlation coefficient R. A very strong positive relationship. Right. Almost perfect, but there are some other factors at play. Okay. They've done another one talking about the distance they live and the number of days they arrived late. Okay. It's a bit all over the place. Describe the form and direction. I would say a weak negative relationship. Correlation coefficient was far out. That makes me think that the last one's a bit wrong. Well, it's probably moderate. Weak might be a bit harsh. I'll say moderate. Correlation coefficient is calculated at minus 0.84. This is form and direction. My goodness, apologies. Scrap that. Form talks about linear or non-linear, and direction is linear, so this would be a negative linear relationship. And then the correlation coefficient is decided as 0.84. That actually means it's a strong negative relationship, which surprises me because looking at it, I wouldn't think that. Is the reason that I suspect that they left strength out of the last one, because it doesn't look like it. It probably wasn't a particularly fair question otherwise. Okay, so we have a study, one based on hours of study and their study score. Okay, there are 2 missing points, these two, so that's 2 and 32. That's 30, 31, 32. And 6 and 44. Cool. This is the least squares regression. Interpret the slope. So for each increase in one, is this on average? Yeah, it's per night. In 1 hour of study per night, study score increases by 3.38. Cool. Interpret the y-intercept. If you did not study, your study score is estimated to be 24.36. Easy. Sketch. Oh, I've got to go back to this one. Sketch the least squares regression line. All right. Well, I'll change colour so it stands out a bit. So the study score is 24.36, so we'll say that's about there. and we can find another point. So let's just do a random point. We'll do, I don't know, 6 times 3.38 plus 24.36 gives me 44.64, which is about maybe slightly higher where that one was. And then I'm going to use my ruler, which is an old textbook that I keep lying around. And I would draw a line straight through there. And is it just worth 1 mark? It is. Otherwise I would label it. I'll do it anyway. Study score equals 24.36 plus 3.38 times our study. Right? Easy. Use the regression line to predict the score for a student that studies 1.4 hours per night. So again, I'm just using this here. Instead of 6 though, it's 1.4 plus 24.36 gives me 29.092, so 29.09. It's only worth 1 mark, so I don't need to write any working out. Would this be considered to be a reliable prediction, yes or no? If I look at my data, my lowest data point is actually 0, so it's within that data. I would say yes, due to it being interpolation. Remember, extrapolation's outside of our data set, interpolation's within. A study score of 43 was predicted. What was the value of x? So that's basically saying 43 equals 3.38 times x plus 24.36. Right, which gives me 3.38 times, what am I doing? I need a minus 24.36 from 43. That gives me 18.64, and then I divide this by 3.38, which tells me that they studied for 5.51 hours, which is a lot. But if you want the good scores, that's what you got to do. That's everything. Anyway, hope that was helpful. Have a terrific day. Thanks, everyone. Bye.